So I wanted to give a description of what you need to do for project 2, which is the Blum Blum Shub project. So you're going to be implementing some parts of the Blum Blum Shub algorithm. In particular, at some point in the code, you need to add this line, which is sort of the heart of the whole idea, um, which is that the n plus first number in the sequence is just the square of the previous number mod n. Mod m, where m is the product of two large primes, and the two primes are congruent to 3 mod 4. So I've done most of it. We talked about it in class. I'm just going to go through it again so you have this sort of video permanent record of things. Before I look at the code, let me show you a little bit about the GMP big number library. So the problem with just using ordinary int data type for this project is that ints are usually, a standard int in C or C++ is 4 bytes, which can give you a number up to 4 billion. But the security of Blum Blum Shub rests on the fact that it's impossible to factor m, which is the product of the two primes. So it turns out that any number up to something like 750 bits can be factored within a reasonable period of time. So an integer in C or C++ is like 32 bits or 64 bits or 128 bits. So they're just nowhere near. They don't have anywhere near enough resistance to factoring to really have a secure pseudo-random number generator. So we have to use this big number library, and it's just, it just helps. Oh, I made some mistakes here. I guess I'm talking as if it were simple. To be honest with you, learning to use GMP is a little bit of a task. But the good thing is that you can make numbers as long as you want them to be in various number bases, and for the most part, it's pretty convenient. All the multiplication, division, addition, subtraction, and modulus and things like that have all been overridden. There are also special functions for like modular exponentiation, something we'll talk about later in the course, and computing modular inverses, and special functions like the GCM and the LCM and other number theoretic functions that are useful for doing cryptography. So this is just a toy program, and I'm going to run it here. And all it does is print the number, but it just shows you sort of how easy it is to work with these things. If you want, you could interpret this as a number base 16. This second parameter is the number base. So if you're reading in a number in hex or something, then, so the number is a little bit different when you regard it as a hex number. And you can do the standard operations like add it to itself. You could declare another one of these things, num2. You can use this constructor where you just put the string right there, and then you could do num times num2 could be the thing that you output to the screen. Right. So they're fairly easy to work with. So now you notice that I have to include these two libraries, GMP and GMP for C++. And when I do the compile command, I have to link to the libraries, but otherwise it's not such a big deal. So let's go back to the files, and I'll go up a directory, and let's look at the code. So mainly what you have to do, what am I looking at here? Oh crap, this is the one-time pad project. Sorry, I'm in the wrong folder. Project 2. So basically what you have to do is you have to modify the code in this file bbs.cpp so that this test is passed. And like I explained in class, I've got some parameter values for the thing set up here, so you don't need to worry about how to compute a large prime or multiply them because I've already done that part. This p is a big prime. This q is a big prime. Um, by the way, if you know, whenever I say by the way, it's bad news, right? You could do create. Do I already have a Sage worksheet in here? Yes, I do. So the Sage worksheet actually is much better for dealing with prime numbers and large numbers because Python has arbitrarily large integers. And but let me just give you an example of what you can do with Sage. There's a built-in function called isPrime. So I'll check it on this number p. Right now it's doing some kind of primality test. I'm not sure how it works, but it's possible that it would have been wiser of me to use a function like, I think there's one called isProbablyPrime. Anyway, so, okay, it's finally done. All right, so it's true that this number is prime. Right. I don't know if that was a probabilistic test or not. Can you give me some help here, Sage? Is probably prime? Huh. I think maybe there's one called next probable prime. Is that right? Yeah, next probable prime. Anyway, we'll play with that later. And so let's get back to the code. Here's P and here's Q. Here's their product M. X is the initial state. So if you look at Blum Blum Shub, this process has to start somewhere. And so the value that you start at is x0. I'll also call it the seed value. So here's the seed value, and notice that this is a property of this object k, which is of type key, which is a type that I defined myself right here. So the key just stores m and p and q and x, and so that's in the object itself. There's also a variable x. But the x in the project on line 25 here, that gets updated as the process goes on. So initially x is the same as the x that's stored in the key, but then the difference is that as you iterate through the Blum Blum Shub random number generator process, this x is going to be updated to whatever the current state of x is. Whereas this one is going to be some kind of unchangeable reference version. So I probably should have declared it as like type const or something, you know. This x is there because if we encrypt something with Blum Blum Shub, we need to be able to decrypt it later. That means we need to be able to generate exactly the same key stream that we used for the encryption process, which means that we have to keep track of what the initial seed value was. So when we encrypt something, we'll generate a key stream, but anybody who knows these numbers on line 14 can generate exactly the same key stream just by redoing the Blum Blum Shub process. And so these things are sort of functionally the key if you want to use Blum Blum Shub as a stream cipher. Okay. So this just checks that basically I didn't make a typo when I was putting these numbers in. And this test hasn't given me any problems, so I think it's all right. Okay, so this next state function is something that you have to implement yourself, and the next state function basically does this. So you know, to get from the previous state to the next state, you have to do this, and so it's not very hard to translate that into C++ code. So I expect that part of the project to be pretty easy. So these test values x1 and x2, that's just what the answer should be, because I have already implemented this myself and then deleted the answer. So your state should agree with my state. I'm defining what I got to be the right answer. You know, there's a small probability, a vanishingly small, infinitesimal probability that I did something wrong, in which case you better hope you made the same mistake as me, or else I'll give you an F. All right, so after that, on line 30, we declared that we passed the next state test. And then we also have this function called stream byte. So that just gets a byte worth of key stream. And so I get a couple. It turns out that this is what they should be. So Turns out that the first one should be 113, the second one should be 30. And so if you can change this function so that it outputs those numbers, then you pass. Please don't do something silly like just making the function return those numbers. I will actually look at what you wrote there. But there's really just one missing line, this line on 115. There's some documentation here that tells you more about what you need to do. This unsigned char C is the byte that gets returned. You know, when I say byte, I'm going to use an unsigned char for a byte. So initially, all of its 8 bits are set to 0. So you should think of this char as being 1, 2, 3, 4, 5, 6, 7, 8, just 8 zeros in binary. And we're going to go through and put a bit in each place, starting from the right and going to the left. Where are we going to get these bits? These bits are just the least significant bit of the current state of the Blum Blum Shub thing. Okay? So when you do next state, you fix that in the first part. So now x, every time you call next state, x gets updated to the next number. And we get the least significant bit by doing mod 2. And then I have to extract the bit in this kind of silly way. I just didn't want you to have to wrestle with the MPZ syntax. But basically what this does is it gets the least significant bit as an MPZ class, and then it immediately converts it to a char. And what you have to do here is some kind of logical OR. You have to use bitwise operation, logical OR, and bit shift and put it together in the right way. And basically you have to put the bit into the right slot in the variable C. Okay, what's next? You got the stream byte. Now it's time to encrypt a byte. So the difference between encrypting a byte and getting a stream byte is that you just XOR with a plain text. So let's look at encrypt a byte. So it's left totally blank, but I think it's extremely straightforward. What you have to do, you basically just take the XOR of this input and a stream byte. So in this function, you're going to call get stream byte in order to encrypt this byte C. Right. So that will, yeah. So if you encrypt 50, it turns out the answer should be 196, and so those are the values that you should get. And now you're going to test the encrypt buffer function, which just calls encrypt byte over and over again. So all encrypt buffer does is you get this C style string here, which you can think of as just, you know, some amount of memory. Len tells you how much memory there is there, you know, the length in bytes. And this is the initial state that you should use. So I include that as a parameter because if you have encrypted something, you need to sort of reset X to decrypt it. So this allows the user to switch to decrypt mode by providing the right initial state. Now you just go through and byte by byte, you encrypt all the bytes in the buffer, and you should be overwriting them. That's good practice in cryptography, and it also makes the code simpler. All right. So what are we doing now? You have passed the encrypt buffer test. So you have roses are red, violets are blue. What are we doing here? Testing. Oh, okay. So this is what you're supposed to encrypt. It turns out that if you do it correctly, this is what should come out. And you pass that. Oh, now it's going to test it for decryption, but it should automatically work for decryption. Notice that the initial state gets reset to the true seed that we saved in the key data structure. So it's going to reset the seed. Oh, you know, I realized something. Something a little funny here. Oh, you know what it is? It's because I used KX for this one and for that one. So that's why it'll work. What I was worried about is that before we got here, next state had already been called several times. So, but don't worry about it. Okay, and that's all. That's it. And maybe just for fun, we could go through and look at some of the other functions. This generates the key. So I wrote this little function called get prime, and m is just the product, and then you get the initial seed. This is the constructor. It lets the user declare how many bits of security that you want. So what does that mean for us? That means how big is the prime. So the number of bits, the number of security bits is just the number of bits in the primes. This generates the key, and then you show the user what came out in some big numbers. I make sure that the number of security bits is a multiple of 8 just for convenience. Next state, get seed. So with this gets the seed value for x. You don't have to do anything with this. In fact, you could just stop listening to this video completely right now if you have no curiosity about the rest of the program, but maybe you should also drop out of college if that's the way you feel. You get x here, and x has to have certain conditions that they describe in the Wikipedia article, which I'm checking here. If you look, it says that the seed should be an integer that is co-prime to m, and it's not 1 or 0. So I just the chances that any of those things would happen with numbers this big are practically 0, but I check anyway. Let's look at the get entropy function. So this is where the actual randomness comes from. So you can read the documentation. But basically what it's doing is it's reading from dev urandom, which is the mix of random numbers that's generated by the hardware random number generator, dev random. So these are cryptographically secure numbers. And I just read them. This is not super hard, right? Yeah, see the main line right here, 183, what's happening is the urandom is getting read from. So I read one character of randomness, and then I add it to a string in hex. And so what it returns is a string, which is a hex string representing a random number. That's what get entropy returns. And back here, that string gets pushed into a constructor for one of these big number types, and it's told that it's base 16, so it turns that randomness back into an integer. This generating primes is something we're going to talk about later in the semester, but if you want a sneak preview, this uses the Miller-Rabin probabilistic primality test, and there's a lot to say about that, so we'll just not mention anything. And that's all. All main does is it declares one of these things and then calls the test function. You can play around with it some more if you want to. By the way, I was thinking this would make good extra credit. You see this part at the end here? Instead of, like, let's say that you want to know what the 100th x should be, instead of doing this Blum Blum Shub process 100 times, it turns out you can go directly there. So, the Blum Blum Shub is not a practical cipher because it takes too long to work with these very big numbers. But this would be a good property because it means that you can produce different parts of the key stream can be produced in parallel. So you can kind of pre-compute it. Different processors can compute different parts of it. Another thing is that you can do random reads of encrypted data. So if you only care about like what happens around the 500th megabyte of your encrypted file, you don't have to generate the whole key stream up to that point. You can go right there. So I will give you some extra credit if you can implement this. You need to find some way to find the least common multiple of p-1 and q-1. That's all you need to know about this lambda. I mean, you can read about it if you want to, but buyer beware. There are two different things that are called that are named after Carmichael, several things that are named after Carmichael, and I just don't want anybody to get confused. So if you want to do least common multiple using MPZ, you have a little bit of research ahead of you. MPZ t LCM. So let me at least point you in the right direction. So this would be the function to use, but this takes an MPZ type, not an MPZ class. So you can call also this ROP. This is C, not C++, and what happens is the result gets returned in this variable. So you have to use an MPZ type instead of an MPZ class. If you want to research this, I mean, it's not going to be too easy, but also not going to be too hard. Maybe this project is too easy. So for those of you who want a challenge, you could do like MPZT hello world and kind of get some feel for how to use the MPZT. And you're also going to need to copy an MPZ. You're going to have to copy P-1 and Q-1 into an MPZT type, and this will explain to you how to do it. It's going to require a little bit of thought. I apologize. Who am I to make you think, you're only taking a college class? And that's all. And yeah, maybe we can get together and see what the right values should be for some of these. Like, I'll produce the 100th one. We can use that value to see if yours is right, etc. And that's all. I'm going to stop the video. Good luck on the project.